So good to be here. And I am a professor of computer science from Kettering University. And we are located in Flint, Michigan, which is an hour north of Ann Arbor and Detroit area. And I'm sure you have heard of this name because it was in the recent news with the Flint water crisis. I'm sure you have heard in that context. I've been here 25 years and I work in the area of localization of wireless sensor networks. And I wanted to present to you, first of all, an overview of this area and what's going on and why this is very important. And it's exploded so much in the last 30 years. And especially in the last 5, 6 years, there's been a huge explosion because of the IoT technology going up, and there are sensors in IoT and in autonomous driving, etc. So I'm seeing a lot of very busy work, very busy publication coming up. And so I wanted to share the overview of the area and the techniques that we use for localization and talk about some of the results that I have in this area. Um, so first of all, the agenda, I'm going to start with definitions here. Let me just get my. So I'm going to start with defining what wireless sensor networks are, just for the formality and for completion. And then I will talk about what localization means in the wireless sensor network and why it's important, and are we able to localize, and how far, and what does localizability mean? And then I will also illustrate why localizability techniques can change, localization techniques can change quite a bit with respect to how we deploy these sensors and where they're deployed and what the assumptions are of the deployment. And you will see there are numerous ways to deploy these sensors. And then once we go through that, then I'll talk about specific techniques. There's been a lot more techniques than what I'm showing today, but I want to focus just on range-based and anchor-based techniques, which I will define both these terms along the way. And then I'll conclude with, having illustrated a few techniques, I'll conclude with where the current research is and what the future holds for this area. Let's start with what wireless sensor networks are. These are a set of sensors that are deployed in various devices in order to basically provide with huge number of applications such as surveillance, and you can do environmental monitoring, monitoring underwater, looking for things under, in the ocean, under the ocean. So basically you embed sensors, which are very small devices, or you can use it for rescuing missions, such as landmines. You can provide home care, or you can track objects, moving objects, such as, autonomous cars and things like that. So the sensors, being small and being easy to deploy, have found their way in various applications all throughout. So the essential job of the sensors is to sense certain information, whatever they're intended for, and then there are a collection of them which then form a network, and then the information is gathered at each sensor, and sometimes they work cooperatively between the nodes in order to get results for the application that we have. So here are a few applications that's shown. As I said, it's been exploding. We can use the application of sensors in industrial robots, industrial applications, in agriculture, animal tracking, environmental monitoring, entertainment, of course, security and surveillance. Nowadays, our phones, everything is equipped with sensors, and one can then collect information of sensors and process it for various purposes. Now, one of the things with sensors, as easy as it is to deploy, it's also limited in its ability to compute. So they are characterized by, they have, by the way, they do have a computational capability, which is a limited computational capability. 8-bit 10 megahertz for slow computations is expected. That's how they're characterized. And they have some battery power, but energy harvesting and energy is very limited in a sensor. Again, we want it to be this way so we can deploy it quickly and collect information. And of course, we have some limited storage capacity. And obviously, we don't want computing to be very long, intense, so that we want to make sure that we get the information out using the transceiver. So this is really how sensors are characterized. They have limited computing capability, limited energy, limited storage, and they're equipped with transceivers where they can receive and send signals. they have a limited lifetime battery. So now, what is localization in this network and what is localizability? So the idea is that once you deploy these sensors, they don't stay in the same place. They move place to place, especially if you're trying to deploy it on in a war zone and stuff. There's a lot of movement going on. And you want to eventually find the sensor so you can go and do the rescue mission, or you want to be able to locate the geophysical location of these sensors. And since they never stay where they are and they tend to move, we want to be able to find their location after a period of time or periodically during the mission. And if you deploy them in a 3D space, obviously this localization is said to be 3D localization. Or if you deploy them on a, in a 2D space, we call it 2D localization. 2D has received a huge number of attention. 3D, there are some work going on, some new work going on with 3D localization. Now, you might say, why don't you equip each of these sensors with GPS so you know their location anyway, so the localization problem gets automatically solved? And the answer is quite simple. GPS consumes a lot of energy, and these sensors, all sensors cannot be GPS. We'll see very soon, some would be, and those would be called anchors. So what is then localizability? How do we go about it? What kind of information is given for us to find the location of these sensors once they're deployed? So it turns out that when we say we want to localize at a wireless sensor network, actually what we're talking about is localizing the underlying graph. So we'll be having some terminology with graph theory along the way. So every wireless sensor network then can be viewed as with an underlying graph with the vertices representing the sensor nodes that we've deployed, and the edges. It's interesting that the edge and the edge weights become what we call the signal range information. And sometimes these edge weights are available, sometimes they're not. When they're available, we have a good collection of edges to work with. And essentially, these are estimated Euclidean distance between one sensor and the other that they can actually determine by themselves by sending signals back and forth between each other. Obviously, we know clearly that there is something called a radio range for each sensor, and they cannot communicate beyond the radio range. So they can pretty much see or exchange information with sensors that are nearby, which then form the set of edges for that particular node. Now, so we really don't know where these sensors are located, and our job is to try to find the exact location of these sensors given this abstract information of a list of sensor nodes and possible edges between some of them. So localization of a wireless sensor network turns into localization, unique localizability of this graph with the given vertices and edges. And there's some support from graph theory, which we will sort of refer to, which is the wireless sensor network graph, or the underlying graph, is localizable. That means we can find the unique location if and only if the underlying graph is globally rigid. And we will define globally rigid in a few slides down the line. There's a graph theoretic property that one can verify. And if that property is verified, then it becomes localizable. Again, it doesn't mean that we can localize it in polynomial time or anything. It just makes it that it's possible to localize. And we'll see why this global rigidity property is pretty severe, in the sense that not every network we come across will be globally rigid. So we have to overcome the issue that what if the underlying graph is not globally rigid, because we would like it to work on random deployments of wireless sensors. So as I said, in general, we would like to assume that the networks are randomly deployed and not deployed according to some global rigidity property. But we would still like to use the global rigidity, probably for a subgraph of the graph, so that we can get started with the localization of the sensor nodes. So, so obviously, if you have a randomly deployed WSN or wireless sensor network, it may not be localizable. But even then, we would like to localize as many as possible. So the performance of a localization algorithm can be measured by the number of nodes that one can localize. And often there could be errors in the ranging information or the distance information, or even the computation of the localization algorithm. So accuracy finally can be compared with some sample of ground truth, and accuracy becomes then important for the geolocation of these nodes. And of course, the more restricted the structure, the less qualified the algorithm is. So you want to work on random networks as much as possible. But if you require your algorithm to have a specific structure for the WSN, then that limitation is definitely would be figuring into the performance. And time complexity becomes important. We want the algorithms, of course, to converge in reasonable time because these are self-localized stuff. So we want to localize often enough. So we would like to make sure the time complexity is good. And if we use any additional assistance, for example, sometimes you could send a mobile robot if it's possible, where in the geographical area where we expect the sensors were deployed, and then maybe use the assistance of the mobile robot in order to, we'll see one such example that can actually localize the network. So now I would like to move on to, so we defined what localization is, which is finding the geolocation of the nodes, and localizability is, which is things need to be globally rigid, and it's an if and only if condition. So the graph has to be globally rigid in order to be localizable. Now we'll talk about how various deployment assumptions exist in this area and how one can, the algorithm can depend on the various deployment assumptions that we have. So I'd like to define two terms, a technical term before I talk about, because this will be coming up along the way quite a bit. So the word anchor, we talked about sensors not knowing where they are, not equipped with GPS. We do equip certain nodes with GPS, not all of them, and these special nodes could be called anchors. These help us localize the unlocalized nodes in the network. And anchors are also referring to nodes that happen to know their location a priori and they stay stationed. So it's possible that we have some sensor nodes that do not move and some that tend to move during the mission. So we could use the ones that we know the location of, even though they may not be equipped with GPS, as an anchor. So that's what an anchor is for an algorithm. A range is a word that's used to actually refer to the estimated distance between nodes that is obtained by using the radio range information of the sensor capability. So nodes can send receive signals with other nodes within the radio range. And for the purposes of this particular discussion, I'm going to assume that all nodes have the same radio range. If they do have different capabilities, we could use the minimum, etc., for the algorithm to still be applicable. So the range refers to the estimated distance between the nodes. I use the word estimated because often there could be some errors in these techniques. So you may not know the exact location, which may then propagate throughout the algorithm and make it difficult to localize. So range refers to the distance that is computed between nodes using, there are several technologies that one applies. One is the received signal strength, which is the simplest technology that is available. So we could use RSSI technique to find the range between nodes, or we could use time of arrival of a signal or time difference between arrival of a signal. So these are some of the techniques that I use to estimate the range or to find the range between two distance or range between two nodes. Now, here are some of the assumptions. There could be even more than what I've listed, but these are the ones that we've come across quite a bit. One is, do we assume that the algorithm has any anchors at all? Are there any nodes at all? Or is it completely anchor free? The deployment sometimes may not allow for any anchors to be available. Therefore, we would have to deal with the anchor free situation, in which case we use something called a hop count. So we talk about number of hops because we really don't have the distance information, any kind of anchor here. Range free basically means that there's no distance information at all between any two nodes. Range based is when we have distance between information available. Sometimes we have angle of arrival of a signal between two nodes available. So in addition to range, you might have an AOA information, or sometimes you may not have the given AOA information. Now, during the algorithm, are the nodes mobile or are they stationary? That's another discussion that we have. So we have mobile sensor networks and a stationary sensor network. This is just during the execution of the algorithm. Do we allow the nodes to move or not? Then we, of course, I mentioned assisted localization. Do we use any kind of robotic assistance that can add distances between nodes that can help localize? Or do we just not assume any kind of assistance during localization? Again, I mentioned about noise in the range measurement. Sometimes we assume that the range measurements or the distance measurements are noisy, in which case we have to incorporate for the noise propagation into the algorithm. Now, indoor localization is a completely different area where if you're localizing with sensor nodes indoor, even though they may be geographically close, within the radio range, they may not be able to talk to each other due to obstructions. And if you're on different floors, that can change things in 3D localization with respect to how the sensors can communicate with each other. Underwater localization has its own challenges. So all of these are assumptions under which various deployments under which we'll study the localization problem. So next thing I want to talk about is the algorithmic techniques, which could be centralized or distributed. Centralized simply means that all sensor nodes give information to a sync node, and then the sync node then can compute the location of each node. Distributed is each algorithm. Each node, of course, computes its own location. Sequential versus global simply means that does every node, do we progress node by node localizing, or do we simply use a global algorithm to localize the entire network? Again, sparse is a very interesting case where it's very difficult to localize sparse nodes efficiently, but there are quite, some algorithms that also constantly work on sparse networks. Dense networks tend to be easier, obviously, because there's more nodes available for communication and for global information exchange. So now that we talked about, we know what range-based is, what anchor-based techniques is, I'm going to go over a few very interesting techniques that have been deployed and just talk about some of my results in these areas, in these applications. So a very well-known technique for finding the geolocation of a node is geometric. It's called trilateration. It's simply that when you have distance available to 3 points in a 2D plane, we're talking about 2D localization here again. So if I know the location of P1, it's X and Y coordinates. So if I know the location of P2 and I know the location of P3, and I have an unlocalized node A, which I know the distance to these three, D1, D2, and D3, because I have the range information from A to these 3 nodes, I can immediately localize A simply because it's a solution to a quadratic equation, which is simply the distance equation between the 2 points. So this technique is called trilateration, which helps us localize a node as long as we have distance to 3 other nodes, which are already localized or they're anchors. So trilateration is a technique that has been used quite a bit in combination with other things individually. So generally, when one uses trilateration, you start with anchor nodes, and then you try to find a node that has edges to 3 anchors, obviously. Then you localize that node, and that becomes now an anchor node again. So we keep adding anchor nodes to the network. So once that location is determined, the non-anchor node now becomes anchor, and then you continue with the next node and the next node. So it's a sequential algorithm where you try to trilaterate. Of course, the success of trilateration is limited in the sense that the number of anchor nodes, it of course depends on the number of anchor nodes. If you don't have enough anchor nodes, you're not going to find enough nodes that are adjacent to the anchor nodes. And obviously, it's the position of the anchor nodes. If they're all clubbed up in one single location, it may or may not help. They may have to be spread out. It really depends on the structure of the sparsity of the graph and the sparsity of the anchor nodes and the order in which you localize the nodes. So you can get stuck. Basically, you can get stuck in this process, in this trilateration process. So what does one do then in order to overcome that? There's the things called trilateration graphs, which, as I said, this sort of limits what kind of networks we can work with. But there are specialized graphs called trilateration networks, which have a trilateration ordering, which guarantee a trilateration ordering, which of course are localizable using the trilateration technique. So the next thing is, what if trilateration stops? Can I do anything else? And the answer is yes, there is a technique called bilateration, which is somewhat helpful in its original form, where we have, which means that I have a node A. However, I don't have 3 nodes that it's adjacent to, because if I have 3 nodes that it's adjacent to, I can trilaterate it anyway. So I only have 2 nodes that I know, whose locations I know, like P2 and P1, that it's adjacent to, which gives me 2 possible locations for this node A. I still cannot know which one is right, but it's an intersection of the 2 circles. I do know the 2 locations that it's adjacent to. Having these 2 locations that it's adjacent to, can that help me figure out along the, if I proceed further, how to localize the node A? The answer is it's been done for things called wheel graphs, which tend to be special graphs in this area, special networks, which happen to be globally rigid. So for example, it was applied to wheel graph, and then the wheel graph was used as a basis to localize larger graphs, to bilaterate larger graphs. So in this example, for instance, if I know the location of V0 and V1, I know V2 is adjacent to those two. So there are two possible locations for V2. I may not know the exact location of V2, but I can find two possible locations of V2. Using those two, I can then find four possible locations of V3, because using those two and its distance to V0, which of course is an anchor, I can then find 4 locations for V3, then I can find 8 locations for V4, 16 locations for V5. But the minute I see the V5, V1, I can then localize V5 immediately out of the 16 locations. I know which one is right because now it has this constraint in addition to its distance to V0 and its constraints coming off of the other 3. Therefore, once V5 is localized, I go back and localize V4 and V3 and V2, and we're all done. So wheels can be localized using bilatration. And bilatration again works only for bilatration networks, which means that the graph has to be like a wheel. And then there's some theorem that combines 2 wheels, so that can help localize a bit larger set of graphs. So my result in this using trilateration, bilatration that I came up with, or we came up with, was that what we call a negative knowledge bilatration. And the goal was to get away from bilatration graphs and work on regular graphs, first of all, regular meaning random graphs. So in a random graph, if I use trilateration, and of course trilateration is going to stop at some point, can I then proceed with bilatration and negative knowledge bilatration? So the way the negative knowledge bilatration works is, I know the distance of A to 2 localized nodes P1 and P2, but I don't have a third node in order to trilaterate. I call the node A bilaterable. Once it becomes bilaterable, then I look around the radio range of the 2 locations. The first location, let's say PA. If I find a localized node there, a localized prior using trilateration or something else, I know this distance doesn't exist, because then A would be trilaterable. If this distance doesn't exist and it's within the radio range, the correct location for PA must be PA prime. If I can find such a B, then I can localize A at this point. Similarly, if that doesn't work, then I look around PA prime and see if there's a localized node around it. If it isn't, then I go back and I say the correct location is PA. So this negative knowledge helps me actually localize more nodes than the original trilateration. So this is not restricted to the bilateration graphs. It can work on a random graph as long as we find. So implementing that algorithm gives us this kind of result here. This is just a random network because I didn't want to just use a bilateration network, a random network generated with radius 10 on a 100 by 100 net on a space, and that's what that looks like. And radius 10 is considered to be very small compared to this area, and it's considered a sparse graph. So the focus is on sparse graphs that's random, which is the challenging aspect of this localization techniques. And then the performance-wise, just using trilateration on this random graph led to this kind of number of percentage of localized nodes was about 15% or 18%, but then we jumped up to 55% by using the negative knowledge bilateration technique. And there's a couple more techniques in the negative knowledge. I showed you one, but I have 2 other theorems that help me continue the bilateration process. So we were able to significantly improve on a random network using the bilateration technique. And so that's the trilateration bilateration, which is what we call sequential algorithm, which is sequential procedure. And the next set of techniques are component-based, and we did some work on component-based techniques. So I just want to introduce what a component-based technique is and then talk about our results again. So instead of localizing each node at a time, how about we localize an entire component at a time? So if you want to localize a component, the component has to be globally rigid as per the theorem that only globally rigid components are localizable, or globally rigid graphs are localizable. So just to show you what global rigidity is and why it relates to localizability, this particular graph is not rigid because there are 2 ways to draw this. There are 2 geolocations for the nodes that respect the distance of the edges. Again, this is called flip ambiguity. This is called generically rigid because I can flip one node to the side and still maintain the same distances between nodes as the original graph. So there are two ways to draw that. So it's not globally rigid either. This graph is globally rigid. There's only one way to draw this. And it's easy to check whether a given graph is globally rigid. When I say easy, I mean there's a polynomial time algorithm for that. So in 2D, so we can check if a graph is globally rigid. This one happens to be globally rigid, and therefore there's only one way to draw that or localize it. There's unique localization for it. So when we talk about component-based localization, I want to find components that are globally rigid and then start localizing them and then work on finding other components and probably merge them together. So the first work that came out in terms of component-based technique was that if you had a component that you figured out was globally rigid and there were 3 anchors in it, obviously we could get a global map of this area with all the other unknown nodes localized. But if you didn't have 3 anchors, then one anchor was outside, that would work as well with the edge in there. You could localize it using a rotation matrix. And similarly, if you had just one anchor and 2 additional anchors outside the globalized area, one can still localize all the nodes here globally, or we needed 4 anchors. So how does one find the initial globally rigid region? Was that they used trilateration. The authors of this paper used trilateration. They started with a triangle, which then they created a local map for the triangle, and then using trilateration, they started localizing using this local coordinate system. And then once the anchors were found, then you would go ahead and move to global map. So you had a local map for the area, and then you would move to a global map using one of these 4 techniques. Again, this suffers from the number of anchors. If the number of anchors is sparse, and it depends on where they're located, you may or may not be able to localize these globally rigid regions and get into a global map. So in this area, our results included some new theorems to find large rigid regions, first of all. So we wanted to make sure that we were able to find as large a rigid region as we can, so that just 3 anchors in a larger area is likely and it's sufficient to localize large global regions. And if you recall, the region they found was based on trilateration. We did not use trilateration to find a large rigid region. We used this sort of merge theorem, which I call rigidity rigid clusters. So we said if two regions are globally rigid, we proved that if you had 3 nodes in common between the regions, then the entire region, the union of the regions, become globally rigid. Similarly, if you have 2 vertices in common, but just 1 edge between them, that's sufficient to make the entire region globally rigid. Or if you had just 1 vertex in common and 2 edges between them, then the entire region was globally rigid. Or if you had 4 edges in common between them, then it became globally rigid. This I call 2-merge theorem, which is because it helps us merge 2 regions. And our results were based on, we started with looking for wheels using 1-hop regions. Once we had the wheels, we know wheels were globally rigid, and then we started merging the wheels together using these 4 merging conditions above. We found really large globally rigid regions, and all we needed was 3 anchors within that globally rigid regions. We ran a multidimensional scaling algorithm with 3 anchors per region. And here are the results of that performance. Again, 10 is a very sparse graph, and then 19, as we go, it gets denser graph. And this is the number of nodes that we localized using this 2-merge algorithm. And what's more interesting is the average number of rigid regions that we found. As you can see, we almost find like only 1 or 2 rigid regions, which means we can localize with about 6 anchors, 3 per region. So by the time you get to dense graphs, you just have a single globally rigid region because you're starting to merge them very effectively. So then we moved on to what I call a 3-merge theorem. So we knew how to merge 2 regions, but what if none of those conditions met in order to merge, because we needed 4 edges between regions in order to merge. And if you didn't have 4 edges between regions, you cannot merge those 2 regions. But are there better ways to merge? And the answer was yes. We found a 3-region merge, which requires 7 edges with some specific conditions. So you can see the 7 edges in here. And if these edge conditions are obeyed, then we say that the R1 union R2 union R3 becomes globally rigid. And that theorem was proved. And then with 3-merge, of course, the results were even better. Once you start merging 3 regions together, As you can see, the number of nodes localized is almost 100%. We get to about 100, all nodes localized by the time we get to 19 to 22, which is a denser graph. For a sparse graph, we still do very well with the range of 12. Here is a performance. The pink shows the merged regions, and you can see that almost every node, in fact, not almost every node is in a single globally rigid region called 3 merge. If we merge 3 regions at a time. Finally, I wanted to just show assisted localization technique which we used, which is we knew that we wanted a globally rigid graph, but if the random graph was not globally rigid, we said, can we add some of these edges? And of course, they are not within the radio range, so they are not able to communicate with each other. So we send a mobile robot that can, there's a technique that can help localize the nodes, or as it moves, it gives 3 different distances to each node that needs additional edges. And with using very minimal number of edges, we were able to make the graph rigid. So once the entire graph becomes rigid, then we could use 3 anchors and use multidimensional scaling in order to localize this entire network. So again, the focus has been on just dealing with random graphs, not assuming any particular thing about the network, structure of the network, which makes it very useful in deployments. Finally, since I mentioned multidimensional scaling, I just wanted to talk a little bit more about it. It's basically a centralized technique, or it could be a distributed technique, where we have to give distances between each node, and then it, it minimizes the error to find a map of that entire set of networks, a network that we give. And obviously we don't have all the distances. So for the distance that we do have, we provided. The ones that we don't have, we could use the shortest path length. Of course, MDS has some error built in because we are providing the shortest path length, and one can talk about the accuracy of MDS localization, etc. MDS has also been tried in the distributed setting, where we could have a node with 3 adjacent nodes. So it could run an MDS at each node here, because it's adjacent to 3 nodes. It knows the distance to these 3 nodes. It's a classical MDS. Iterative MDS would mean that F would run MDS for CDF, and E would run MDS for ABE, and then they exchange information to make a global map between the 2. So iterative MDS and classical MDS can help just make the algorithm distributed rather than stay centralized. So MDS can be used in both distributed setting and a centralized setting. So that really is basically an overview of localization and some techniques that relate to range and anchor-based algorithms. And the reason why there's been already about, in the last 5 years, there have been several survey papers in this area, which indicates that it's quite an exploding area. And because sensors are now inbuilt within the IoT, and IoT has become, sensors are in every single small devices that we see. And so therefore localization is gaining a lot of attention right now. And with autonomous driving, there are papers relating to localization and autonomous driving. And object tracking and localization have things in common, and tracking has become a part of, localization techniques can be applied. Machine learning is now starting to be used in order to localize with some limited results. And we would probably see more machine learning application localization being applied using machine learning algorithms. So that is really, and now I want to open up for questions, and thank you for the opportunity to present this.